Welcome students to our online lecture series of design of steel structures. In today's lecture, we will learn regarding the classification of cross section of the steel sections as well as numerical based upon it. For classification of cross section, clause number 3.7, page number 17 of IS 800/2007 is utilized. A brief theory regarding the cross section. A plate element of a cross section may buckle locally due to the compressive stresses. This local buckling can be avoided before the limit state is achieved by limiting the width to the thickness ratio of each element subjected to the compressive action, low force, movement, or a shear. If you observe the diagram, the box column and a I section column, the buckling of the I section column can be seen very adversely. So this effect we have to nullify it. So the section need to be checked for the cross section. In plastic analysis, the member shall be applicable to form the plastic hinges with sufficient rotation capacity, that is ductility, without local buckling to the redistribute bending moment before failure mechanism occurs. In elastic analysis, the member shall be capable of developing the yielding stresses. The section can be broadly classified into 4 types, that is plastic, compact, semi-compact, and slender. These classifications, again I say that, are available on page number 17. The first class of the section is plastic section. Plastic sections are the section which can develop plastic hinges and have a rotation capacity required for the failure of a structure by formation of the plastic mechanism. Hence, the structure doesn't fail suddenly because of the plastic hinges and the rotation capacity. The second section are the compact section. The compact sections are the one which can develop the plastic movement of resistance but have inadequate plastic hinge rotation capacity for the formation of an plastic mechanism. Hence, for design of any structure, plastic sections are preferred. If not, compact sections are referred. Then the semi-compact section, the cross sections in which the extreme fiber in compression can reach yielding stresses but cannot develop the plastic moment of resistance due to the local buckling. The last section is the slender section, the cross section in which the element buckles locally even before reaching the yielding stress when the width to the thickness ratio is greater than class 3 becomes under this category. When different elements of cross sections fall under different classes, the sections shall be classified as governed by the most critical element. If we compare all these 4 sections, plastic sections are more preferable for the design of steel structure. From figure number 2, which is on page number 19 of IS 800/2000, this is our rolled steel beam section or I section, which can be utilized for the design of beam and column. This is the channel section, this is the angle section, this is the T section. These are the built-up sections, I section. Then again rolled steel T section, then compound element, that is T section with a plate at the top, and second T section with a plate at the top which is greater than its flange. The intention to explain this figure is that while classifying the section, we need small b, that is width of the flanges, small d, effective depth of the section, tf, that is thickness of the flanges, and thickness of the web. If we see in the diagram, the small v, it is nothing but the half the width of the I section, and the small d, it is the distance between root radius 1 to root radius at the bottom. Here the thickness of the flanges are eliminated. If we compare with the I section with the channel section, here B is total width of the flange, height is same as that of our I section. Then if we see the angle section, here one leg is designated by small b and another leg is designated by small d. Thickness is designated by the T. If you observe the T section, here the D, that is total depth is taken, but width of the flange is half the width and the thickness remains the same. Same in the case of built up section. Now if we look at the table number 2, which is utilized for the classification of the section, here it is divided into 1, 2 and 3 columns. The column 1 is nothing but the compression element, which gives us detail about the compression elements which are being utilized. Column 2 gives us the ratio of small b to T, and column 3 is sub-classified into 3 types, that is plastic, compact and semi-compact section. Here if our I section is utilized, then we have to select the row number 1. Here I have underlined row number 1 with a red line. The first criteria is B upon TF. If you look at the diagram, B upon TF, that is the flange criteria. If the ratio of B upon TF is less than 9.4 epsilon, then the section is classified as a plastic section. If this value of B upon TF is in between 9.4 to the 10.5 epsilon, then the section comes under the compact section. And if the value is in between 10.5 to 15.7 epsilon and greater than 15.57 epsilon, the section is classified as a semi-compact section. Then the second row deals with the welded section. If you observe in the diagram, B is the half of the total BF. In our steel table, the BF is given the total width of the total width of the flange. Here we have to take the half the width of the flange. This is very important point while classification of the flange criteria. Now the welding section, as told previously, welding sections, here are the welding section. B is taken the half of the width, but here the ratio should be less than 8.4, then it is a plastic section. 9.4 it is a compact, and 13.69 then the section is the semi compact section. Then the neutral axis at the middle depth, that is the web criteria. The web criteria is taken as the ratio of D upon TW. If the ratio of D upon TW, D is the depth of the section. In the diagram, if you observe, the D is the effective depth. That is, here we subtract the width of the thickness of the flanges from both the ends. Hence, the section, the small d is calculated. If this ratio of D upon TW, that is the web criteria, if it is less than 84 epsilon, the section is plastic. Less than, if it is greater than 84 and less than 105 epsilon, the section is compact. If it is greater than 105 epsilon and less than 126 epsilon, it is a semi-compact section. Then for the channel section, if you observe the D upon TW, the ratio is taken as 42, and the 42 ratio is been followed throughout the section. Then in the case of the angle section, there is no depth or the width. Here directly we are taking small d to the thickness, that is T, of the angle section. If that ratio is less than 42 epsilon, the section is taken as a plastic section. Then if the angle sections are placed back to back, and then in that case the ratio of D upon T, if it is less than 94 epsilon, the section is taken as a plastic section. If it is in between 9.4 to 10.5 epsilon, the section is taken as a compact section. If that ratio is between 10.5 to 15.7 epsilon, the section is taken as a semi-compact section. In the next slide, we will be learning the numerical on the design of steel, classification of the section. The first example is on classification of a. Therefore, our first numerical is on the design of our I section, which is ISHB 400, about 77.4 kg per meter. If we see this section, we have to calculate from the steel table. We have to write down the properties of the section. I suggest all the students to utilize a standard steel table. I will prefer to say that utilize the steel table published by Ramamurtham under Dhanpat Rai publication. Now, this first section, ISHB 400. If you look in the steel table, there are 2 to 3 sections which are having depth 400. But we have to select the one whose weight is 77.4 kg per meter. Now, we have to write down the steel table properties. From the steel table, the properties of the section. H, that is the depth of the section, which is equals to 400. BF, which is nothing but the width of the flange, it is 250 mm. TF, it is the thickness of the flanges, it is 12.7 mm. TW is the thickness of the web, which is equals to 9.1 mm. R1 is the root radius 1, which is equals to 14 mm. Now we have to calculate the small d. That is equals to H1. H1 is equal to small d is equals to total height, that is H minus 2 times the thickness of the flange plus R1. Hence, our small d is equals to 346.40 mm. Epsilon. What is the epsilon? It is nothing but the ratio of square root of 250 divided by Fy. Now, as we have assumed that our Fy of the section is 250, hence our epsilon is equals to 1. Then we have to calculate the small b, which is nothing but the width of the flange. Width of the flange is equals to, here if you observe the diagram, width of the flange is taken as half. Here small b is equals to half of BF. So 250 divided by 2, it is equals to 125 mm. Then the outstanding element of a compression flange, which is nothing but the ratio of B upon TF. Here the ratio is shown B upon TF. So we are taking this ratio 125 divided by 12.7, it is equals to 9.4 epsilon, and the ratio is 9.84 epsilon. This 9.84 is greater than 9.4 epsilon and less than 10.5 epsilon, if you observe the table, the ratio is greater than 9.4 epsilon and less than 10.5 epsilon. Hence, our wave is, so flange is compact. Then wave of the section, that is neutral axis at the middle depth, we take the ratio of d upon tw. The d upon tw is equals to 346.40 divided by 9.1 mm, and it is 38.06 epsilon. If you look into the table again, it is less than 84 epsilon, hence our wave is plastic. But even though our wave is plastic, but our flange is compact and we are going to the lower side, hence therefore the section is compact section. The second example is for Indian standard medium channel section of depth 300 mm, about 35.8 kg per meter. From the still table, we have to write down the properties of the section. H, that is total depth, which is equals to 300 mm, BF 90 mm, TF 13.6 mm, TW 7.6 mm, R1 13 mm. As that of our I section, here we have to calculate the small d, that is H1, which is equals to H minus 2 times of thickness of flange plus R1, and hence we have got our small d or small h as a 246.8 mm. Thereafter, we have to calculate the epsilon, which is the ratio of under root of 250 upon Fy, and as our section is having Fy equals to 250, hence our epsilon is equals to 1. Now here there is difference between I section and the channel section. In the case of the I section, we have to take BF, that is the width of the flange, half. Here the BF of the channel section is totally need to be taken as it is. Hence the outstanding element of a compression flange, the ratio of B upon TF, so 90 upon 13.6, and this ratio is less than 9.4 epsilon, hence the flange is plastic. Then the wave criteria, is ratio of D upon TW. We got the value as 32.47 epsilon, hence the wave is plastic. Again, if we look into our still table, into table number 2, for the channel section, the wave of a channel, this row is utilized, and for the I section, the wave criteria, this row is utilized. And as our both the elements, that is flange and the wave, are the plastic, hence our section is plastic. Then our third numerical, that is classification of the angle section. Here we have taken a angle section of 150 by 150 by 12 mm, having the weight of 27.2 kg per meter. This section which we have utilized for the classification is equal angle section. Here we have to use still table again for writing down the properties. But in the case of angle section, all the properties are in front of us. From the section only we can understand what are the properties, that is small d, small b, as well as the thickness of the flange. Here leg of the angle B upon T, it is a ratio, the ratio is in between, it is greater than 10.5 and less than 12.5 epsilon. Then D upon T ratio, it is again less than 10. As it is angles equal angle section, the same is been followed, and hence our angle section is semi-compact one. Dear students, this is in this way we have to classify eye section, channel section, and the angle section. One thing which we have to keep in mind, if our web is plastic and flange is compact, we have to write down that, or the section is compact section. Always go for the lower version. So on this note, we will conclude this lecture, and in next lecture we will meet again. Thank you.